Hi, welcome to the first of a whole series of paleontology lectures I'm posting here on YouTube. My name is Russell, and I'm at California State University, Chico. And these are a series of lectures for my invertebrate paleontology class. These lectures I'm posting in hopes that folks can look at them before class, so we're not wasting time giving a lecture, just some background information for the class. And each week I'll talk about a different phylum of invertebrates. No dinosaurs. These are invertebrates, but we'll cover a different phylum each week. And then the idea is in the class, we can actually do the hands-on portion. So if you're not in the class and you just stumbled on these videos, I hope they're useful. And just let me know what I could do to make them more interesting for you. Well, this week we're starting off with taphonomy or fossilization, because before you can understand any of these fossils, invertebrates, or even dinosaurs, you have to understand what the fossil is and what information you can get out of the fossil. And so taphonomy is that study of fossilization, and fossilization is the fossilization process. Now, what I'm not going to get into today is how fossils are made. To me, that's something I'm going to do in the lecture. I'm going to save that for the folks. And so the fossilization process includes things that happen like are those fossils there in the first place? What are the impacts of their living environment, or what's called the biocenosis? Or when the critters die and they fall to the seabed or the swamp floor or wherever there you find the fossils eventually. Um, in the rock record. What happened to them as like after they died, but before they got buried, and that's known as thanatocenosis. The picture a cow stomping a bunch of other dead critters before. Not that cows are mean by any means. It's just the first thing that came to my mind. But you know, you would find those fossils as crushed things because of that activity. Once they get buried, then there's all kinds of geological processes, which we call diagenesis, for kind of low temperature shallow burial. Or if you're really caught up in mountain building episodes and a lot of changes to the rock, you may even see metamorphism. Super exciting stuff, and I'm not going to talk about it. You have to come take my class to learn about that. So today we're going to focus on the nouns, on the types of fossils. And so in order to do that, let's look here at our happy clam. It's dead. You might not think it's happy, but it is happy because he's going to get a lot of attention today, and he's going to be studied by us. Because once you pick up a fossil and you learn how that fossil is made and you understand the process of fossilization learned through these nouns we're going to go through, the types of fossils, they each tell you different information, and it's really cool. And so to me, it's absolutely as important as knowing who you are when you find a fossil, or how old you are when you're a fossil, but really understanding what you are. What are you made out of? And that is the fossilization process. So to start with, we see this is a clam that's buried in sand. And there's many, many ways that we can eventually extract this clam from the rock record and understand how it's been preserved. And you may have heard of some of these terms. I'm going to go through them all. First of all, the first one, it might just be the original shell. We've seen fossils that are 100 million years old that are preserved as the original shell. Totally cool. We forget that that's an option. Um, Often we see the internal mold, or we just see the external mold of a fossil. We might find a cast where the whole fossil is gone, but the sediments or the cements in the rock layer have actually modeled it perfectly. Sometimes we do find the shell or the bone or whatever, but it's been recrystallized or replaced, or in the case of bone and wood in particular, permineralized. So the pores are filled with another kind of mineral. They might be preserved as a carbonization or a compaction. We think about this in terms of plants in particular, or it might be something cool like an incrustation. In fact, there's a whole lot of these special cases, unique things like, say, amber, that are maybe not as common in the rock record, but when you find them, they tell an immense amount of important information about the geological processes. But for now, let's cover the big ones. And so we could take this clam, as I mentioned, you could take this shell and analyze under a microscope and realize, good Lord, I've got the original material, the original shell. And depending on what kind of invertebrate, because again, this is invertebrate paleontology, what kind of an invertebrate shell that is, that might be some form of calcium carbonate, which we write for shorthand as the calcium and the carbonate together. And calcium carbonate is found as two kinds of minerals. The easy one, like those lazy critters that are like, oh, just take the CO2 out of water and the calcium from all this dissolving basalt. And it's the easiest mineral I can make? I just don't have time. I'm kind of lazy. It's aragonite. Aragonite is the easiest calcium carbonate mineral to make. You want to make a little stronger mineral than aragonite, you take that same calcium carbonate, twist its mineral shape a little bit, and you can form calcite. And the interesting thing about calcite is some of this calcium has magnesium, or it switches, sorry, magnesium for calcium. And so you can have calcite with a lot of magnesium or just low magnesium. And that break is like somewhere around 3 to 5%. So it's not a lot. If it had a lot, it'd be dolomite. That's another class. I'm not going to worry about it. These are the main calcium carbonate minerals. There's also a lot of fossils who living organisms, the original shell, it's a little harder to make, particularly in the ocean. A little easier in rivers or lakes, is made out of silica, glass. The equation for that is SiO2. There are some other minerals you might find. Some of these animals make their shells out of phosphate. Super hard, super resistant, nice fossils, but it takes a toll because there's not a lot of free phosphorus around in order to make phosphates. But all of these can be found as the original shell. Now, what is really common though, is that organisms, maybe not the phosphate guys, but the other organisms build their shells out of a material that's easy to build. They only really need it to last as long as they're alive. And so it'll eventually break down. And so we can see a change where that original shell might turn into a new material. And we can see this under a microscope because the shell looks the same, but as we identify the kind of mineral, we know from biology, at least the biology of modern organisms, that that's not the mineral it was supposed to be. And so it can be recrystallized. And the main way that we see recrystallization is maybe going aragonite to calcite, or the original silica is, say, a mineral or mineraloid, they call it. It's not really organized, called opal. And that opal, where the silicate are, the silica tetrahedra are kind of more randomly oriented over time under burial, those shell can change. It can recrystallize from unorganized opal to organized microquartz. And so if we find microquartz, we know that an organism has changed into a new form. Now, that's recrystallization, taking the original mineral and tweaking it and changing it. I don't know if this is a good analogy, but imagine if you burned toast. That burnt crust, it wasn't like it came magically from outer space and substituted. You just turned that bread to burnt stuff. That's kind of like recrystallization. That's really different from taking the original shell when it's buried and dissolving it and replacing it with a totally different mineral. And again, we recognize this because we can find the fossil, we can dig the fossil out of the ground, and we can look at its mineral and go, that I know that organism, it doesn't make its mineral out of X. I know it originally made it out of Y, so it must have replaced it. It must have dissolved and replaced it with a new mineral. One of the more common replacements we find is where calcium carbonate dissolves, maybe because the groundwater is a little acidic, and instead that hole will get filled with a silicate mineral. So silica replacing carbonate is common. The opposite can happen. You can also have other minerals, other phosphates, pyrite, lots of other kinds of minerals replacing. Again, the trick is saying that fossil is made out of a mineral that I know wasn't the original mineral, or it wasn't a changed form of the original mineral. And so we have replacement. So already we have three terms: original shell, recrystallized, and replacement. Now, Let's go back to the burial part of this. Our clam was buried in sand. We see that sand because it made a lot of dots on the board, and dots are sand. Let's say that over time, as the animal rotted away inside of its shell, more dirt just fell in through the cracks. So we replace it with, no, sorry, we fill it in with lots of little dirt here. Okay, so now we have dirt on the outside, dirt on the inside. Now imagine over time, this rock comes to the surface and it gets cracked. In fact, let's mess with this little guy first. Let's take the original shell. Let's take the recrystallized shell. Let's take the replaced shell and dissolve it completely. With the magic of a finger, I can erase all that stuff. All right, so now we see our empty shell. Now imagine if we broke it, okay? That top part, if we moved it over, crack it, and it goes like this. Okay, and then this inside of the shell, that's going to pop out because we removed the bottom. And so that inside of the shell, it's going to look something like this. So we have the rock that was the outside of the shell, the rock the inside of the shell, and we have to use the formal term. And so what we've said is that we've on the inside of that rock surface, you can see a mold. My brain wants to say cast. It's not cast, it's a mold. We see a mold of either the outside surface of the shell or the inside surface of the shell. In the first case, that's known as an external mold. In this case, we have an internal mold. And so now we've just added two more types of fossilizations. Now, for a lot of invertebrates, the inside and the outside look pretty different. And so you can definitely find that imprint in the rock record and go, oh, I see that's an external mold of a trilobite or the internal mold of a snail. Sometimes it's pretty hard though. I mean, there's certain organisms that the outside and the insides, because there's just a thin shell of mineralized material, their skeleton, it's pretty hard to tell apart. So you do the best you can. I should say also there are some plants that are hollow on the inside. A lot of us have experienced bamboo. We know cracking bamboo open, it's hollow. Well, you can get internal molds of plants. They can be pretty common with some plant groups. Okay, so we have original shell, replacement, recrystallized, internal, external mold. Let's do a crazier one now. And this actually happens. And let's pause for a second. The reason why I'm going through all this is because when you find the fossils and you describe it, just as important it is to say what the name of the critter or the type of fossilization, I'm sorry, the name, I just gave you the answer. It's important to say who it is and how old it is, but knowing the type of fossilization is going to give you a lot of information about how the fossilization process occurred. Okay, so you've got this, it's recorded, so you could pause and go back because I'm going to erase this stuff. And to do that, I'm going to use my magic of my sweatshirt. Okay. Now, here's our external mold. Imagine the external mold in the rock record gets exposed and more minerals or more cements get bound up to it. And so they fill in completely mimicking that surface. And now, maybe this is made of cement that's a little harder or another kind of sediment that's harder. Now we dissolve away the original external mold using the magic finger. And now if you found that fossil on the ground, think about it. It would look just like the original shell, at least the outer surface of that original shell. But what would have been shell isn't shell, it's dirt or it's cement. You've actually casted the original fossil as the same thing as if you like poked your fingers into some kind of a putty and then filled it with plaster to make a cast of your fingers. And that's the term we use. It's a cast, and fossils can be preserved as casts. Pretty cool. In fact, why don't we take a break and let's look at some of these fossils and see what they look like. All right, let me show you examples of some of these fossils. This one here is a beautiful example of the original shell preserved. It's an ammonite type of a cephalopod mollusk. And what I'm hoping is shown in this light here is that the shell has this beautiful mother of pearl, even though this is over 100 million years old. And if we were to analyze that, that rainbow hue is aragonite. And aragonite doesn't normally last in the rock record. Remember, as I said before, it's a weak mineral. Doesn't need to last long, just it lasts as long as the critter's alive. But in this case, it gets preserved. Here, we have some fossil clams that are about 5 million years old, still pretty old, and again, still the original aragonite. So preserved as the original mineral. Now, I should say right now, there's a caveat, recrystallization, which is the changing of one, say, calcium carbonate to another calcium carbonate, or one silica to another silica, like aragonite to calcite or opal to microquartz, is actually really difficult to see without a microscope. I don't think you can actually do it. So I'm not going to show you any examples of that. But what I do know is that this is a coral, and that reddish color you see is not paint. This is a coral that we know from biology had to have made its scale from calcium carbonate, but it's been replaced with jasper, with a kind of reddish opal, reddish silica. So that's replacement, and it's beautifully preserved. You can see all the original features of the coral in that silica. Here's another example. This is another coral. It's a colonial coral, a beautiful polished cobble, totally replaced with silica. And again, we know that it was originally made of calcium carbonate. State Rock of Michigan, you know what it is. You know what it is. I don't need to tell you, and you can Google it if you don't know and look smart that way. Okay, so that's getting into some of this mineral stuff. What about the casting features? I said on the picture, you can tell the external mold from an internal mold because of the features of the skeleton. Here's some examples. And again, sorry if this doesn't look out great on the video, but I'll try. This is a scooped out depression of a trilobite fossil. And so there's no shell there. This is an external mold of the trilobite. Similarly, this is where there was a brachiopod, a thing that's kind of like a clam in looks, but biologically not at all like a clam. But again, it's a scoop. The shell scooped in and is now gone. And so this was an external mold of that surface. Now, the internal mold of an actual clam looks like a clam. You can see the clam shell to it. This is all dirt, though. There's no shell there. And if we look really carefully at this, and I can't do this with this kind of a camera, but what we can see is features of the inside of the shell, what's called the mantle, the line, and we can see where some muscles have attached. And so we know that muscle would have been attaching to the shell, and the shell is gone. And so this is an internal mold. These two internal molds are a little easier to see. This is an internal mold of a clam. Imagine if I step back. My two hands are a hinged clamshell. And if I hinge over this clam and then I release the clam, the internal mold, this is actually fairly common because, as I've said a couple times, animals make their skeletons out of really weak material. So if it fills in with dirt and it gets hard, and then over geological time, that aragonite dissolves away before it can be recrystallized or replaced, it's pretty common to find these internal molds in some deposits. And we use the German name Steinkern for a specific kind of internal mold for a bivalve. Here's another one that's kind of easy to tell because it's a snail. Let's make it a right side up snail. Because if you think about a snail inside of a shell, it's going to live up in that shell. It wants it to be smooth. It wants that body to go in, go out real easily. You're not going to see a lot of bumps and pokey things. But on the outside of the shell, it's going to be flamboyant. It's going to have all kinds of spines and crazy things and ornamentation. And so if you find something that looks like a snail, but it's nice and smooth and coiled, you've probably preserved that internal mold. This is an extra bonus, by the way, because that's not just the internal mold of the shell. In fact, you can see a little bit of the white shell preserved there, but the actual internal mold has also been replaced with silica. So it's a twofer. It's been replaced with silica and it's an internal mold. Now, as far as some of these other ones we have, casts are a little difficult to tell, but I found this one as I was poking around the little collection behind me. That's the edge of an ammonite. An ammonite is, again, here's another ammonite. It's one of these coiled cephalopods. In this one, I can tell that it's coming out. It's the outer surface. It has the ornamentation, that ribbing that is typical of some ammonites, but it's not shell material. It's all dirt. So this was a cast of where that original shell was. Now, what I left off of here were some of those special cases. And one example of a special case is being replaced with a mineral that's from a pretty unique geochemical environment. And so it tells us something really unique about maybe the pH of the waters or the temperatures of the waters, or whether the waters were oxidizing or reducing. And one of the more common ways we see this, again, I hope this shows up in the light, is with pyrite. Here we see an original fossil has been replaced with iron, sulfur, pyrite. And pyrite is an interesting mineral because it doesn't like to be oxidized. It rusts really quick. And so if we're finding a fossil replaced with pyrite, we know that at least this part of the fossilization process happened under reducing conditions. Now, one of the terms I threw out at the beginning was carbonization, which is what we often refer to for leaves that get preserved not in 3 dimensions. The leaf is gone, but the carbon in the leaf has left a beautiful imprint on the rock. Sometimes we see bones preserved this way as carbonized imprints. There's actually a really nice metasequoia. Been listening to interesting stories about metasequoia lately. Really cool plant. Here's one other example of a pretty interesting kind of a fossil. One thing you will learn about me during this series is while I truly do love all fossils, I mock dinosaurs, but let's face it, dinosaurs are cool. My favorite fossil is the stromatolite. It is the most important fossil in the entire fossil record, bar none. But this is a fossil of a stromatolite from the Eocene, maybe about 35 million years ago or so, up in Wyoming. I don't know the exact number. And what it is this stromatolite. We'll learn loads about stromatolites later, but think of stromatolites as layers and layers and layers of growth. In this case, of maybe bacteria and cements and mud that grew on top of something. And in this case, it grew on top of a log. And so it is an external mold of that log. In fact, I can see the beautiful detail of the wood grain preserved in that log. However, because it is not so much the dirt that made the external mold, but something encrusting it, like the bacteria that formed the stromatolite, we call this type of fossilization an incrustation. So it's one particular kind. Here's another one. These are a series of grass roots that are from the Miocene. These are about 15 million years old, and they are encrusted by also bacteria. In fact, this one in cross section, you could see the reed, like maybe the bamboo kind of a grass, was in the very middle, and then these bacteria encrusted around it and cemented it as a kind of preservation. So that's a start. There's other examples we could talk about, like amber is a special case. We go on and on and on. And I'll give you a list of some of those to maybe think about and Google up and be interested in thinking about it. The key thing about all these cases, and this is the main point I want to make, is that you want to learn the type of fossilization and record that with your fossil because it tells you the history of what happened to that organism after it was buried and all that time before you touched it, before you got it out of the ground again. And in many cases, that history of burial and turning into a fossil studied through taphonomy gives you as much information about the ancient earth as the fossil itself. There you go. Hope you enjoyed this first broadcast. Now go look at your fossils and see if you could tell what kind of fossilization they went through.